The winter of 1944 laid a frozen shroud over the European theater, transforming the battlefields of France and Belgium into a bleak expanse of frozen mud and shattered timber. Beneath the overcast skies, the American armored divisions faced a terrifying mechanical reality. The backbone of their armored force, the M4 Sherman tank, was bleeding out in the freezing fields. Designed for mass production logistical simplicity and infantry support, the Sherman was a triumph of industrial standardization. Yet it was fundamentally outmatched in direct engagements against the heavily armored predators of the German Wehrmacht, namely the Panzerkampfwagen 5 Panther and the Panzerkampfwagen 6 Tiger. The standard American 75mm gun and even the upgraded 76mm M1A1 gun fired armor-piercing capped ballistic capped projectiles designated as the M62. Weighing just over 15 pounds and leaving the muzzle at roughly 2,600 feet per second, the M62 relied on sheer kinetic energy to punch through enemy armor. But the German metallurgical engineers had shifted the mathematics of survival. The Panther tank featured a frontal glacis plate 80mm thick, sloped at a steep 55-degree angle from the vertical. This aggressive geometry effectively increased the line of sight thickness to 140mm of Krupp cemented steel. When an American standard armor-piercing round struck this sloped glacis at typical combat ranges of 800 to 1,000 yards, it did not penetrate. Instead, it fell victim to the shatter gap effect. The intense kinetic energy of the impact combined with the compound angle caused the hardened steel cap of the American projectile to deform and fracture before the main penetrator body could bite into the armor plate. The round would disintegrate into useless fragments, bouncing off the German hull and leaving the Panther completely operational, while the American crew sat exposed and vulnerable to a devastating counterstrike from the Panther's standard 75mm long-barreled gun. The crisis reached the desk of the United States Army Ordnance Department and the National Defense Research Committee. They needed a projectile that could travel faster and hit harder without requiring a complete redesign of the tank turrets or the breech mechanisms of the existing guns. The solution did not begin on a military proving ground but inside the industrial laboratories of the General Electric Company, specifically its subsidiary the Carbolloy Company located in Detroit, Michigan. To understand the genesis of the American countermeasure, one must look away from the battlefield and into the molecular structure of one of the heaviest and hardest elements on the periodic table, tungsten. Tungsten, extracted from raw ores like wolframite and scheelite, possesses the highest melting point of all discovered metals. In the decades prior to the Second World War, the industrial world recognized that when powdered tungsten was mixed with carbon and subjected to extreme heat, it formed tungsten carbide, a compound possessing a hardness that approached that of a diamond. General Electric had heavily invested in this technology during the 1920s, entering into complex patent agreements with the German industrial giant Krupp. Under these pre-war cartel agreements, General Electric and its Carbolloy division tightly controlled the American market for cemented tungsten carbide, which was utilized primarily for machine tool cutting edges. The material allowed lathes and milling machines to cut steel faster and deeper than ever before, fundamentally revolutionizing mass production. However, the cartel arrangement had kept the price of tungsten carbide artificially high, restricting its widespread adoption. By 1940, the geopolitical landscape had fractured and the United States government initiated federal antitrust indictments against General Electric and Krupp to shatter the patent lock. Under the leadership of metallurgists like Cy Jeffries, the Carbolloy Company rapidly expanded its production capabilities to meet the insatiable demands of the wartime arsenal of democracy. Tungsten carbide was desperately needed to manufacture the artillery shells, airplane engines, and rifle barrels required for the war effort. The same extreme hardness that allowed a Carbolloy tool bit to shear through raw steel on a factory floor in Detroit made it the perfect candidate to shear through the face-hardened steel armor of a German Panzer in the frozen forests of Europe. The engineers at General Electric, working alongside military ordnance experts, theorized a revolutionary concept for anti-tank ammunition, the high-velocity armor-piercing projectile, officially designated as HVAP. The physics of armor penetration dictate that kinetic energy is equal to 1/2 of the mass multiplied by the velocity squared. Because velocity is squared in the equation, increasing the speed of the projectile yields a vastly greater increase in penetrative power than simply increasing its mass. However, standard gunpowder charges in the 76mm gun could only push a 15-pound steel shell so fast before the chamber pressures exceeded the safety limits of the breech mechanism, risking a catastrophic explosion that would kill the tank crew. To increase the velocity without exceeding the pressure limits, the overall weight of the projectile had to be drastically reduced. Yet a lighter solid steel shell would lack the necessary density to punch through heavy armor, simply shattering upon impact. The WWII design solved this paradox through composite engineering. The core of the new M93 WWII round was a solid dart of cemented tungsten carbide weighing approximately 4 pounds. This extremely dense sub-caliber penetrator was encased in a lightweight carrier body forged from aluminum alloy with a hollow steel windshield fixed to the front to maintain aerodynamic stability during flight. The total weight of the M93 projectile was reduced to just 9.4 pounds compared to the 15 pounds of the standard armor-piercing round. When the firing pin struck the primer, the propellant detonated with ferocious intensity. The lightweight aluminum body allowed the explosive gases to accelerate the projectile down the rifle barrel at a staggering muzzle velocity of 3,400 feet per second, far exceeding the speed of sound and traveling significantly faster than any previous American tank ammunition. The engineering required to mass-produce these tungsten carbide cores was immensely complex. It relied on the science of powder metallurgy. Workers at the General Electric Carballoy facilities began with finely refined tungsten powder and carbon black, blending them uniformly. To bind these abrasive particles together, they introduced a matrix metal, almost exclusively cobalt. The cobalt and tungsten carbide powders were loaded into massive rotating ball mills where they were ground together for days, ensuring every microscopic grain of carbide was coated with the cobalt binder. This volatile mixture was then poured into precise steel dies and compacted under immense hydraulic pressure to form the rough shape of the penetrator core. At this stage, the material was fragile, holding its shape only through mechanical compression. The true transformation occurred in the sintering furnaces. The compacted cores were loaded onto graphite trays and slowly pushed through long electrically heated furnaces purged with hydrogen gas to prevent oxidation. As the temperature inside the furnace climbed beyond 2,500 degrees Fahrenheit, a metallurgical miracle took place. The tungsten carbide itself did not melt, but the cobalt binder did. The liquid cobalt flowed into the microscopic voids between the carbide grains, pulling them tightly together through capillary action. When the cores emerged from the cooling zones of the furnace, they had shrunk in size but increased exponentially in density. They were now solid masses of cemented tungsten carbide, practically impervious to deformation and ready to be inserted into their aluminum carriers. The Ordnance Department rushed the prototype WWII rounds to the Aberdeen Proving Ground in Maryland for exhaustive ballistic testing. The results were immediate and violent. When the high-velocity M93 round struck the test plates representing the Panther glacis, the aluminum carrier and the steel windshield immediately vaporized upon impact, tearing away like tissue paper. The entire kinetic energy of the projectile, traveling at supersonic speeds, was concentrated exclusively into the small frontal area of the tungsten carbide core. Unlike standard steel, the tungsten carbide did not shatter or deform against the sloped armor. Instead, it bit into the Krupp steel, forcing its way through the atomic lattice of the armor plate through sheer, unrelenting pressure. The extreme density of the core acted like an industrial drill bit driven by explosive force. It punched a perfectly circular hole right through the sloped glacis, generating a lethal shower of molten steel spall that would incinerate anything inside the crew compartment. Despite the success at Aberdeen, getting the M93 rounds to the front lines proved to be a logistical nightmare. The entire American war economy was starved for tungsten. Every pound of tungsten carbide diverted to make an anti-tank shell meant one less pound available to manufacture the machine tools needed to build aircraft engines and ship propellers. Consequently, the War Production Board heavily rationed the material. When the WWII ammunition finally began trickling into the European theater in the autumn and winter of 1944, it was treated like gold. The Ordnance Department dictated that the rounds be issued almost exclusively to dedicated tank destroyer battalions operating the lightly armored, highly mobile M18 Hellcats and M10 Wolverines. Standard M4 Sherman crews were considered lower priority and often had to barter, beg, or scavenge just to acquire one or two WWII rounds to keep hidden in their ready racks for desperate emergencies. The psychological impact of possessing the M93 was profound. For the first time, American tank gunners knew they had a projectile capable of reaching out and killing a panther or a tiger from the front at ranges exceeding 1,000 yards. The arrival of the high-velocity armor-piercing rounds coincided with one of the most violent phases of the war, the Battle of the Bulge, and the subsequent push toward the Rhine River. The freezing rain and deep snow exacerbated the brutal reality of armored warfare. Tank crews lived inside freezing steel boxes smelling of diesel fuel, cordite, and unwashed bodies. When an engagement commenced, it was a matter of seconds. An American gunner staring through the crosshairs of his periscopic sight would identify the boxy silhouette of a Tiger tank emerging from a tree line. The tank commander would scream the order for armor-piercing high velocity. The loader, a man working in a cramped dark space while wearing heavy winter gloves, would reach into the protected ammunition stowage, pull the specialized M93 round, and shove it violently into the open breech of the 76mm gun. The massive steel sliding wedge of the breech block would automatically snap shut, locking the explosive energy inside the chamber. The gunner would adjust his elevation, traversing the turret using the hydraulic power traverse, stepping on the firing switch the moment the reticle settled on the thick frontal armor of the German machine. The resulting explosion would rock the entire 30-ton Sherman tank backward, violently compressing the vertical or horizontal volute springs of the suspension system. Before the mechanical sound of the recoil cylinders fully registered inside the turret, the tungsten core was already crossing the battlefield, tearing through the freezing air. The impact against the German armor produced a brilliant white flash of kinetic energy converting to heat. The extreme localized pressure exerted by the General Electric manufactured core exceeded the yield strength of the German steel, forcing a catastrophic failure in the armor plate. As the war dragged into early 1945, the United States Army deployed its ultimate armored response to the European theater, the heavy tank T-26I-3, which would later be standardized as the M26 Pershing. The Pershing was a radical departure from the Sherman, featuring a lower silhouette, thicker cast armor torsion bar suspension, and a massive Ford GAF liquid-cooled WWII engine. Most importantly, it mounted the formidable 90mm M3 gun, a weapon originally designed as an anti-aircraft artillery piece. But even the standard 90mm armor-piercing rounds occasionally struggled against the absolute thickest plates of the heavily fortified German tank destroyers like the Jagdtiger or the heavily sloped turrets of the King Tiger. To ensure total dominance, the Ordnance Department and Carbolloy engineers scaled up the tungsten carbide technology, developing the 90mm WWII-30A16 projectile. The implementation of this massive tungsten cored round was proven during the crossing of the Rohr River and the subsequent armored clashes near Cologne. In the ruined town of Elsdorf on February 26, 1945, the brutal reality of these metal titans colliding was perfectly documented. The 3rd Armored Division had advanced into the town, deploying a newly arrived T-26I-3 Pershing named Fireball to overwatch a roadblock. The night was pitch black, illuminated only by the flickering flames of burning buildings. Concealed in the shadows of the rubble, roughly 100 yards away, sat a German Tiger tank. The Tiger ambushed the Pershing, firing 3 rapid 88mm rounds. The first German shell struck the Pershing directly in the gun mantlet, penetrating the coaxial machine gun port and instantly killing the American gunner and loader. The second round smashed into the 90mm gun barrel, causing the chambered round to cook off and violently distorting the tube. The third shell glanced off the rim of the commander's cupola, tearing off the hatch. The Tiger attempted to reverse out of the rubble to escape, but became hopelessly entangled in the heavy debris, forcing its crew to abandon the pristine machine. The American mechanics recovered Fireball, repairing it within a week, but the revenge of the Pershing came swiftly. Shortly after the ambush at Elsdorf, another T-26I-3 from the same unit spotted a Tiger I and 2 Panzer IV medium tanks maneuvering on the outskirts of the town. The engagement range was approximately 900 yards, a distance where standard American 75mm guns would have been utterly useless against the thick frontal plate of the Tiger. The Pershing commander ordered the loader to chamber the highly prized 90mm WWII-30A16 round. The mechanisms of the 90mm breech snapped shut, securing the massive composite shell. The gunner laid his crosshairs low on the German machine, aiming for the flat vertical plate of the lower gun shield. When the 90mm cannon fired, the concussive blast shattered the remaining windows in the surrounding ruined buildings. The incredibly heavy tungsten carbide core crossed the 900-yard expanse in less than 1 second. It struck the forged Krupp steel of the Tiger's lower gun shield, perfectly bypassing the shatter gap effect entirely. The density and hardness of the General Electric manufactured carbide punched a clean lethal hole directly through the heavy armor plate, instantly neutralizing the German tank and validating years of complex metallurgical research. The success of the high-velocity armor-piercing program was a testament to the silent integration of civilian industrial capability and military necessity. The men who spent their lives studying the grain structures of non-ferrous metals in the quiet laboratories of Schenectady, New York, had directly engineered the destruction of the most feared armored vehicles on the European continent. They understood that warfare was no longer just a matter of maneuver and morale, but a brutal mathematical equation calculating mass velocity, hardness, and kinetic energy. The German war machine suffered from its own metallurgical failures late in the conflict. Cut off from global supply chains, the Third Reich lost access to critical alloying elements like molybdenum and nickel, which were essential for producing tough, resilient steel armor. As a result, the armor plating on late production Panther and Tiger tanks became increasingly brittle. While it remained incredibly thick, it was prone to catastrophic cracking and spalling when subjected to extreme localized impacts. The American WWII rounds perfectly exploited this hidden weakness. Even when fired from extreme ranges where the tungsten core lost enough velocity that it could not achieve complete penetration, the sheer kinetic shockwave transferred by the unyielding carbide dart would fracture the brittle German steel on the interior of the tank, sending hundreds of razor-sharp metal flakes flying through the fighting compartment. The legacy of the tungsten carbide penetrator extended far beyond the muddy fields of the Second World War. The fundamental physics established by the Carbaloy engineers formed the baseline for all modern anti-armor warfare. The realization that a long, dense sub-caliber core traveling at hypervelocity was the ultimate key to defeating heavy armor led directly to the development of armor-piercing, discarding sabot rounds and eventually the fin-stabilized projectiles used by modern main battle tanks today. But in the bitter winter of 1944 and the bloody spring of 1945, the equation was purely visceral. It was the smell of hydraulic fluid, the deafening roar of the radial engines, the clanking of the steel tracks in the frozen mud, and the desperate hope of an American tank crew shoving a silver-tipped carbaloy round into the breach, praying that the mathematics of General Electric would bring them home alive. The detailed reports from the front lines flowing back to the Aberdeen Proving Ground continuously reinforced the tactical supremacy of the WWII ammunition, forcing the Logistics Command to prioritize its shipment across the Atlantic. Convoys dodging U-boat wolf packs carried thousands of these small, meticulously crafted pieces of industrial diamond substitute, ensuring that every tank destroyer battalion holding the line in the Ardennes or pushing across the Rhine had the specific kinetic tools required to violently dismantle the crumbling myth of German armored invincibility. The tungsten, which had been mined from the deep earth shipped across the globe, crushed, heated, sintered, pressed, and machined, had found its ultimate brutal purpose in the freezing heart of a European winter, terminating the reign of the Panzer divisions one catastrophic penetration at a time.